Today I'm presenting our work Parakeet, which is a system for practical key transparency for end-to-end encrypted messaging. And this is joint work with Lev and Alberto, now at Mistin Labs, Esha Ghosh, who is at MSR, and Kevin Louis, Ezran Oster, Sean Lawler, all of them at Meta. So I said end-to-end encrypted messaging. So in this setting, Alice and Bob want to communicate using something like Signal or WhatsApp or Telegram. And maybe they have each other's phone numbers, but to communicate, they need each other's public keys. So the identity provider, which is also the server, has a database of phone number to public key mappings. And in that sense, it's essentially both the encrypted messaging service and that identity provider. And now, even if the encryption is fully secure, the server is trusted for serving keys correctly. If Alice and Bob want to communicate, basically they have to request each other's public keys, and we use usernames for simplicity. But the server can respond with malicious public keys so that, for example, Bob thinks only Alice can read these messages, but instead the server can mount a meddler in the middle attack. And what's worse, this can be done undetected. So the solution for this is what we call transparent privacy-preserving dictionaries. And just as a reminder, in this setting, the server holds a username public key dictionary, and users can join, and so their usernames can get added to this dictionary. They can change their state, so users basically own their username, and they can update the corresponding public keys. And they want privacy, so they want the server, for example, not to give metadata away to users that they've blocked. And the identity provider can actually cheat, because it can show the different views of the public key for the same username queried at different times. This is actually an example of a more general problem where a server holds a dictionary with label value pairs. Another example is a financial ledger that is centralized. So something like FTX, where the central server is trusted for privacy and for ordering, but it's not trusted for serving correct state. For example, the debacle with FTX. So let's talk about certificate transparency or tamper-evident logging or something like that, which some of you may have heard of before. The thing is, due to various reasons, this ends up being a very different set of challenges than the certificate transparency setting, especially because of the privacy. So what are the security guarantees we want? Remember, the threat model is the identity provider holds a dictionary, and it may cheat by showing diverging views to different parties. And ideally, we want to prevent this from happening at all. But this ends up leading to assumptions on clients, something like clients can store secrets, they can protect their secret keys properly, and this causes usability problems. We all know that clients are bad at storing secrets. So instead, we go with non-equivocation, meaning the server cannot show different keys to different clients without getting caught. So, for example, at any given time, if Alice thinks her key is PK Alice, Bob cannot be shown PK bad and have the server get away with it. So this slide is a little bit dense, so please bear with me. Let's talk about the identity provider in this model. Remember, the identity provider holds a database of username public key mappings, and it's trusted for privacy and authentication, which is the case in existing systems. So for example, if you want to join WhatsApp, you get a message to your phone number. So that's how the server authenticates you. What we want is to eliminate trust for the server serving correct public keys. In this model, updates are batched and take effect at discrete time steps, which we call epochs. So there's also users, obviously, and the users can join the system, and later they can update their own public key once they're in the system. They can look up each other's public keys if they're permitted, for example, if they're not blocked. They can check their own keys history, and what they want is that no changes take place without their finding out to their own public key. And then when their friends look up their public key, they should receive matching values to what they believe their own public key is. We also introduce another party in this model called auditors, and their job is just to share some computational burden to make it easy on most clients. So these auditors check global predicates, and This could include, for example, something about the cryptographic state changes over some sequence of epochs, such as the server didn't destroy any records in this period of time. And this could be anyone. So this could be users. So those could be, say, some sort of power users. It could be smart contracts. It could be TEs. It could be other unrelated parties. We'll talk a little more about this later. But because they can be anyone, they should not learn data about particular users from auditing. So I know this slide was a bit dense, but mainly just focus on the bolded and different colored text on here. So you want to eliminate trust for serving correct public keys in the identity provider, and users want no changes to their key happening without their finding out, and that everybody who queries their key gets the correct key. And auditors check global predicates but shouldn't learn anything about particular users. So with this simple model and these high-level details, we can already list what components we need. We need a mechanism for committing to the server's mutating state. We need a mechanism to allow users to monitor their own keys. And we need some source of ground truth. So if there is something getting committed, the user should be able to access this commitment. So you want a way to share the small commitment. And in our system in particular, we want to build it at a global scale. So we want to support billions of users, even those with computationally limited devices. So to summarize, there is an identity provider, has a username public key mapping, and we need a way to commit to this mapping, and we need a way for users to access this commitment at each time step. So we break down the problem as the commitment and verification for the mutating database step and the disseminating small commitment step. Let's talk about this committing and verifying to the mutating database first. So just there's a database and you want to be able to commit to it as it changes. So in previous work, there's been solutions based on various iterations of Merkle trees or other kinds of vector commitments. And we mostly compare with Merkle trees because that's what we use, because they require the least amount of assumptions, and even hash functions have been standardized now, so they're more viable for actual implementation. In terms of reducing user load, other work also includes third-party auditors, and then there's some work that includes something like zero-knowledge proofs in order to reduce the load on users. In terms of users monitoring their own key history, some work relies on what are called append-only authenticated data structures, which are basically preventing the server from deleting the changes that it made and erasing the evidence, which means that no state changes on the server are ever deleted, so the server's memory is ever growing. Or they have users do linear work in the number of server epochs to monitor their own keys, or the server has to generate some sort of expensive zero-knowledge proofs, which if you have millions and millions of users querying at the same time, may not necessarily be viable. So this overall seems like kind of a solved problem, but a lot of practical issues show up when you start designing for the billions of user scale. And I'll only discuss a subset of the problems that we talk about in the paper. And the first of these is state machine replication and separating basically the storage layer and the layer of actually doing the cryptography. A lot of work basically just abstracts this away, and their experiments use basically just one machine. And this is a problem because you can't always load billions of users worth of authenticated data structures into memory and read the entire thing locally to operate on it. So instead, what we do is we provide a flexible storage layer API, and this basically can plug modularly into any distributed database solution. So in terms of practicality, it's a lot more viable. And all you need to do is implement a little bit of Rust code, and you can plug in easily. Then the next thing that this work requires is a data structure for state commitments. And as I mentioned, we use Merkle trees because those have very few assumptions and are pretty efficient. Previous work with the most comparable guarantees grows to hundreds of terabytes over a period of 5 years, as you will see shortly. Of course, this storage cost blow up is quite expensive. And we actually replace this with an underlying data structure that gets all the same guarantees but it's just significantly more storage efficient. So before moving forward, let me just highlight the benefits of our commitment of the database scheme. Here we compare our storage costs with a work called Seamless, which is the closest in terms of assumptions and security guarantees to our work. Seamless has 110 terabytes of storage over 5 years if you have a reasonable 10 million updates daily, which is what you should expect for a global scale system. In our case, we barely make the 5 terabyte mark. So that's the comparison. Now, I showed you this table and I left one row blank, so you're probably wondering what that is by now. So this is basically the mechanism for users checking their own key. And I mentioned this before, you can use zero-knowledge proofs, or you can basically have the users do linear work in the number of server epochs, which is equivalent to them being always online, or have append-only data structures. And respectively, the problems with these are zero-knowledge proofs are impractical for the server, having users be always online or do linear work in number of server time steps is impractical for the client, and append-only data structures are impractical in terms of the fact that they have ever-growing storage costs, which those of you who work in industry can only imagine the difficulty of trying to get someone to deploy something that has ever-growing storage costs. So our work actually finds a middle ground between this append-only paradigm and the clients are always online or doing equivalent of always online work. And we call this a secure compaction. And I want to talk a little bit more about this. So suppose the server is running epochs, a bunch of epochs have passed, several years have passed, and there's a bunch of entries from way before, and they're kind of obsolete by now. So maybe you can just delete them, and you can just have the auditors check that everything that is deleted is actually just from very old logs. But this is a problem because there may be old data that is still relevant. So, for example, Bob may have joined the system and done all of his updates really early on, and his latest key is technically very old, but is still in use. So this shouldn't get deleted, right? So in addition to checking that old enough entries are being deleted, the server could also show that for any deleted entry, some update exists that basically overwrites that entry. And this is a problem because now you're leaking specific users' metadata, and I said the auditor shouldn't learn data about particular users, right? So what we do is we basically involve both individual users and auditors in this deletion process, and we say there's like very few sparse, well-defined epochs where you do deletion-related operations. In particular, you provide a grace period during which values are tombstoned or basically marked for garbage collection. And during that period, users can come online and check that their values are marked correctly, and auditors can check that values that are marked as tombstone are old enough. And only at the end of this period can these tombstone values be garbage collected. So that's all the time I have to talk about the commitment and verification portion. Let's talk about disseminating the commitments themselves. So again, recall, the server commits to this database, and you need a way to serve the commitments as they get updated. So previous work largely places this problem either out of bounds, or they use something like gossip, where users basically come online, talk in some out-of-band mechanism, and basically just tell each other, this is the commitment that I saw. And if it diverges, then they know something went wrong. But this is a problem in a global scale system because you might get network partitions. So for example, somebody in rural India may not communicate with somebody in rural Norway. Users may also come online intermittently, and users may not have the bandwidth or enough battery even to gossip. Remember, we want to support really old or computationally weak devices as well. So overall, this means dissemination may be very slow. What that means is any guarantees are retroactive. So what if we used blockchains instead? I mean, that seems like the solution to everything now, right? You could post a small commitment in a smart contract, or you could use the op return field in Bitcoin. But now you trust the blockchain and its code implicitly. And it's well known that even live clients can be too heavyweight. This is open area of research in blockchains. And prior work has shown that if billions of users query the system, you may end up flooding the network with queries. And then the network basically isn't able to do anything else. So what if we have our own little blockchain that serves commitments specifically for this and other types of transparency applications? But the thing is, blockchains mean consensus. And is consensus really needed in this setting, or is it just overkill? So consensus has a lot of problems, right? It requires lots of communication, leads to delays, and is complex to implement and analyze, as has been shown by a slew of formal verification work and that is ongoing on verifying consensus protocols. So instead, what we say is, let's look at the setting again. The server is trusted for compiling the updates and finalizing the underlying database anyway. And that's what it is supposed to do in this system. And it also has the infrastructure for serving users and maybe even compiling messages from some independent witnesses. So why don't we actually just use independent witnesses, for example, many trusted hardware instances of different companies, or some sort of industry consortium. So basically, these witnesses just store the latest commitment and check that the new commitment built on top of it is okay. So you're not diverging in your chain of commitments. So what does this protocol look like? The identity provider has created a new commitment for the latest epoch. It just tells all the witness nodes that it did this. The witness nodes check this commitment and sign it. And when they sign it, they just forward this to the identity provider, who then collects these signatures and can serve it to clients. So the communication in this type of protocol is only between the identity provider and the witnesses, and the identity provider and the users. Witnesses don't communicate with each other, and users don't communicate with witnesses. And clients accept if a threshold number of witnesses have signed something that they receive. So this type of protocol has similar guarantees in terms of consistency, validity, and termination to BFT protocols. The only thing is you give up liveness, but you get something basically much faster. And you had to trust the server for liveness in the basic original setting anyway. So maybe it's not so bad. In addition, if you don't like this, maybe you can just use this in addition to other mechanisms and just get additional guarantees. And this is simple protocol, easy to implement, meaning fewer bugs. Plus, in terms of actually serving the commitments, you're just using existing server infrastructure, which they had the infrastructure to respond to queries anyway. And in return, users get certified commitments together with proofs for each query, so the guarantees are all basically simultaneous. And here's a throughput latency performance of Parakeet from basically small commodity machines. And even when you have a lot of updates, like something like 800 updates per second, so that's 80 millisecond epochs, that basically leads to less than 5-second delays. So this shows that the commitments certification by the nodes is never going to be a bottleneck in a realistic scenario. So, and also I want to point out that the performance doesn't seem to degrade as the number of witnesses increases. So with that, I'd like to thank you for coming to my talk, and thank you to my awesome collaborators. And you can find our paper on the NDSS website, and all of our code is open source, so you can find the links in the paper as well.
One of the problems with auditing type of scenarios is there's a lag, and there's the requirement that people actually check the logs and things like that. So for example, with certificate transparency, it actually doesn't help you at all if you don't actually go check the logs, right? And it seems to me like your approach could suffer from Merkle tree forking and things like that if you're not careful,
with the auditor. So actually the great thing about our paper, which Seamless, which was the work I compared with, also guarantees, is as long as you have one honest auditor for one epoch, you're actually fine for that epoch. And the honest auditors across epochs can all be independent of each other. So you could even say, like, probabilistically, maybe one user decides to verify the epoch change at one particular epoch, and you're still fine. So as long as there's one honest auditor, you're fine.
All right. I look forward to reading the paper or finding you in a hallway.
Yeah, please.
You had one of the comments where you said that gossip is not good because it doesn't deal with network partitions.
I was trying to instigate questions. Thank you.
Yeah.
It works.
I would claim that gossip, in particular, flooding, is the best you ever can do, which is an extreme form of gossiping, right? So when you replace an underlying, like an overlay that can be designed to be highly resilient, or you just do flooding with 4 witnesses, I would claim that you're still vulnerable to partitions, probably even more with the first, right? So that's one commentless question. Maybe you can say something about it.
Yeah. So that was what I was saying about you can use the witnesses in addition to gossip. So if for example, you don't have the kind of device that can easily gossip, then at least you get some guarantee from the witnesses. You can get additional guarantees from a good gossip protocol. You can get additional guarantees from querying smart contracts. You can even get guarantees from using some third-party website, such as Twitter or Postrade.
And one last comment, if you can show the consensus part again, right? You're saying that that's as good as BFT. If I look correctly here, you're assuming that your identity provider never fails. So you don't trust it, but you actually do assume that it's highly reliable, which means you never really have to do any view change or anything. So you have additional assumptions. And just making sure that that identity provider is actually highly resilient, you will need a consensus for that. You will need some form of backsource draft or something.
Oh, yeah. So this is basically underlying consensus protocol on the, basically like node replication on the server side. But we do have some other things that you can do with your witnesses, which are in the paper for, if you're wondering about, for example, censorship and stuff from the server side.
So that I'm not worried about. I'm just saying is that these, because you're not doing any kind of view change or anything, these cannot fail. Otherwise, you have to select, you have no service. So.
Yeah. So this is, again, still strictly better than what exists.
Yeah.
So
I understand that.
Yeah.